Does two things, and I'll kind of tell you ahead of time what this Part 13 does, and then you can see what I mean. First off, it talks about this idea of spectator ions, and spectator ions are like spectators in the stands, whereas they just watch what's going on the field or whatever. Just so spectator ions also just kind of watch what's going on with regard to a chemical reaction. Then the other thing that this does, and it's not a small thing, is it does a titration problem, but the titration problems we did were they were both in aqueous solution. And you had like molarity and concentration and molarity, and you had to get to concentration or something. This one actually starts out with the analyte, the thing that's being dripped into in the beaker is a solid. So you're giving grams. You're giving grams of the stuff. But it's gonna feel very familiar because we're gonna go from grams. We know we can go from grams to moles, and then it's going to be kind of like a regular stoichiometric calculation. So that's the two things that this does. So electrolytes are something that conduct electricity. So we've talked briefly about two types of compounds. We have ionic compounds and we have molecular compounds. We'll be talking more about compounds. But for ionic compounds, remember those are the ones that have a metal in their formula. And for ionic compounds, if they dissolve, you'll get a metal positively charged cation and a negatively charged anion. And so they'll be floating around there in the water. So for instance, sodium chloride is an example of an ionic compound. If you take sodium chloride, table salt, you dissolve it in water, and if you were to look at the water, you would have, so this is NaCl solid, we're going to dissolve it in water, and then we're going to have our metals. Sodium's a metal. It'll run around with a +1 charge, and our chlorines will have a -1 charge. So this solution is called, it will be an electrolytic solution. When you get Gatorade or whatever, they'll say, drink this because it will give you the electrolytes that your body needs. Because as your body sweats, you lose the cations and anions that you need. So that's it. Ionic compounds dissolve in water. Now we're going to see here, if I were to take a compound that's not ionic, like glucose or sucrose, sugar, and dissolve it in water, you're going to have your sugar particles running around, all dissolved. You won't see it, no sludge, but there's no charge. No charge on those dissolved particles. There's a charge on this dissolved particle. So we get this sort of thing. Here's a figure from your textbook. See, that first one, actually the two little green things, you can think of them as something kind of like sucrose, where it dissolves, but there's no charge. Here we go. Now this one, it might be hard for you to see, but up here I can see this would be like dissolving sodium chloride. I have plus, minus, plus, minus, plus, minus. So just showing you, we dissolved an ionic substance, and it breaks into its cations and anions. So now, actually, it will conduct electricity. So the beauty of this whole thing is, now these plates actually are a surface area where electrical current can pass now through the liquid. So what's the difference between the first one and the second one?
The light is on.
The light is on, yeah. So it creates a path for electrons to flow. This one, no path. Okay, it's like some sort of molecular substance that's been dissolved in water. So what's the difference between the second one and the third one?
Some of the molecules split up.
Some of the molecules split up and some don't, exactly. So what about the light bulb? Very clever.
Dim.
Mm-hmm. The one on the far right is dimmer, yep. So that's trying to show you that there's conductivity, but not as much conductivity as the middle one. So, yeah. The other day, I said that we know an endpoint of a titration by either visual, colorimetric, That's what you guys are going to use. You can use phenolphthalein on Thursday. Phenolphthalein on Thursday. And you're going to look for the pink color, okay? But the other one is conductivity. I said potentiometrically, it's the same thing. So we could look for the conductance of your solution mixture to get your endpoint. All right, so let's talk ionic compounds. So here we have sodium chloride being dissolved in water, thus the AQ. It's splitting apart into the positively charged metal, okay? So remember we talked about periodic table in here, didn't we? Okay. The JAG separates the metals from the nonmetals. So sodium is going to be a cation, positively charged. And then the chloride is the nonmetal, and it's going to be negatively charged.
And that only happens when they dissolve.
Right. That only happens when they're dissolved. So that's a good point. So actually, if we were to take a chunk of rock, just like the sodium chloride, it looks like a beautiful crystalline lattice structure, just a solid chunk. And we're going to put a plate here and a plate here and try to see if we get electrical current. It's not happening because it's not going to conduct electricity in its solid state, just its dissolved state. So there's one. We to be talking more about these compounds, but of course, Ca, what element is Ca?
Calcium.
Calcium. And NO3 is nitrate. So here we have calcium nitrate. And the thing here though is, do you see where NO3 is quantity 2? So over here on the product side, when we show it splitting apart, sometimes this splitting apart is called ionization or dissociation. So we show the dissociation or ionization, notice we have 2 nitrates, 2 NO3 minus. Now, you may not quite know that actually nitrate is got a -1 charge, but we'll kind of get there. It does. So that makes sense to you, hopefully. So if we go ahead and we're going to pick on calcium nitrate. This actually showing the dissolving process is quite clever, I think. The thing about a water molecule, anytime you see a Mickey Mouse thing like that, screams water molecule. The red is the oxygen, and oxygen is a nonmetal and it tends to form a negative charge. Okay, so actually each oxygen is what we call partially negative. And I'm going to go ahead and introduce the symbol we use for partially. It's the Greek letter lowercase delta. It looks like an S, so that's partially negative. That's for my oxygen. And my ears are my hydrogens, H2O, don't you know? And so these are actually, the hydrogens are partially positive. So right away, does that not make sense? I just think it is so cool. That's really what, sometimes we use the word solvate for kind of dissolving something also, you know. So those are like waters of hydration kind of surrounding the chlorine, but it's not just any orientation. It's the partially positive hydrogens that kind of cling to the negatively charged chloride ion. So anyway, here we have potassium chloride. This is the crystalline lattice structure. Put an S here for solid, and here you're seeing it kind of dissolve. It just looks like, I just think it's cute how the little water molecules kind of escort the negatively charged anions. And check out what's happening to the positively charged K. Of course, K is potassium. So up here, the orientation of the water molecules, not so surprising, is that the partially negative oxygens are kind of gathering around the positively charged cation. So that's what happens when we dissolve an ionic compound. Okay, so we're going to work this little problem here. I'm going to show you how to work it common sense, and then I'm going to show you the factor label. It says, what is the concentration of the nitrate ion? Now, if you do a few of these, we want concentration in molarity. So I'll find my nitrate, and I could put question mark molarity. And notice what we're given. We said that the calcium nitrate was 0.230 molar. So 0.230 big M under my calcium nitrate. So if I told you your choices for the nitrate, now look at the stoichiometry here. What if I said in the form of question, is this let's see how we go. 0.115 molar? Is it 0.230 molar? Is it 0.460 molar? How many people think it's 0.115 molar? How many people think it's 0.230 molar? How many people think it's 0.460 molar? Why do you think it's 0.115 molar? Logan thought it. It wasn't just you, Benny. Logan made us that too.
Because of the full thing is 0.230, and then when I split apart, then that's not going to be part of the. It's like part of the full solution.
I can see that. Well, what if I were to tell you that for every one of these units, one of the formula units, calcium nitrate, you get 2 nitrates. And I want to tell you it's not 0.115. What is it then? Yep, 0.460. Yep, it splits. But I know exactly where you're at with the 0.115. And this is how we would do it factor label. So we would have the 0.230 moles of calcium. You have to do the whole thing in this case. 0.230 moles Ca quantity NO3 subscript 2. That's calcium nitrate. 0.230 moles CaNO3 quantity 2 per liter. And then this is where we're going to take the we're going to do a stoichiometric ratio that we have 2 moles of NO3 minus NO3 negative 1 for every 1 mole of Ca quantity NO3 2. And actually, I didn't mean to put you guys on the spot, which of these 3 would be the right answer. That's really when teachers go to make up multiple choice tests, that's what they do. They choose what would be a good, they're called distractor. So you factor 2, in this case it'd be twice as much. So of course then is where we get the answer there is 0.460 moles of NO3 negative 1 per liter solution. So that means 0.460 molar. 0.46 molar NO3 negative 1. So I did this problem to kind of show you leading up to the problem I want to kind of end with here. So it's an ionic compound, it's going to break apart, and that's how it's going to break apart. And we get to the molarity of the ions that way, thinking of it that way. So there's 2 terms I want to throw at you, and it's funny because let's see. What do you call it? The description, we become a dictionary. The meaning of a net ionic equation actually has the term of my other question. So a net ionic equation is a chemical equation that you have removed the spectator ions for. I just think it's weird because you need to know what a spectator ion is. Okay, so the net ionic equation, all a spectator ion is can be described this way. We've been talking about chemical reactions, and on either side of my hand here, I have your reactants, reactionary products. Basically, you know it's a spectator ion if it appears the exact same way over here on the reactant side as it does over here. That's what makes it spectator. It doesn't do anything in the chemical reaction. It's just a bystander. If that's the case, we're going to do an example here as our last problem. We're going to actually take them out of the equation. And now the new equation you have is the net ionic equation. That's it. Sounds like it could be a good term on a test, doesn't it? But somebody said nope. So let's go ahead and draw a picture of this one. This is what I was kind of describing before, where the stuff in your beaker down here is actually going to be a solid, not another aqueous solution. So here's my burette. These are what you guys will be using on Thursday. And here's my stopcock. And it's going to drip out. And here is, I'll go ahead and use an Erlenmeyer flask. That's not a very good name on my class. But, okay. So we are going to put 0.285 grams of oxalic acid down here. So here's my little solid. 0.285, 2585. And I'll go ahead and use the formula of oxalic acid, H2C2O4. I'm going to put an S for solid. But I'm going to go ahead and dissolve it up with about 100 mils. Now the fact that it says about 100 milliliters, you know then the volume's not really critical. But the thing I juice it up with is not pure water. It's 0.5 molar H2SO4. All right. The solution is titrated with, so this is what we call the analyte. The titrant is up here. It's titrated with CHM165 Oct, which is potassium permanganate. It's a purple looking stuff. It says that, I'll go ahead and put it up here, that to get to the endpoint. Now remember how the endpoint works. Basically we are going to drip in, use the stopcock to drip in for potassium permanganate, and the endpoint is when all of this has been used up. And I'm going to show you what the chemistry looks like here in a minute. But in order to reach the endpoint or equivalence point, you're looking at 22.35 milliliters of this stuff. I'll go ahead and put an AQ here because it's dissolved in water. So question mark, what is the molarity of the KMNO4? Right. So I know the next slides will kind of, I'll kind of be a little bit redundant on the board when I do the next slides, but I thought it would make sense to kind of show you the chemistry this way instead of how I do on my next two slides. So the oxalic acid, this is the chemical reaction, H2C2O4. I'm going to do that. I'll put AQ because we're going to juice it up with 100 milliliters of 0.5 molar H2SO4 is going to react with your KMNO4, the thing that's in your burette. I'll put AQ here. And another ingredient for this thing to proceed actually is the H2SO4. I'll go ahead and put AQ here. What's going to be produced is carbon dioxide gas, and you're going to have, I think I'm running out of room, so you just have to kind of go with me here. You're also going to have the manganate Mn plus 2 cation floating around. You are also going to have the sulfate ion floating around, SO4 2 minus AQ. You are also going to have water. I just think it's fun when more water is produced, it just joins the club, probably in its liquid state. And then the last thing I have here is you are going to have K plus potassium ions floating around. Now, one of the things we talked about just a minute ago was if you see the same thing on both sides of the reaction hour in the same form, you can delete them as spectator ions in your net equation. On the next slide, I don't know if you have it already, but I'm going to go ahead and pick on the KMNO4 and then pick on the H2SO4 to show you how it breaks apart like an ionic compound, like an ionic substance would. So for KMNO4, I'm going to have a little arrow up here. I'm going to say it goes to form K plus MNO4 minus. It breaks apart. For the H2SO4, I'm going to do a little arrow. I'm going to say it gives me For H2SO4, it gives me an H plus. Oh, wait. I'll say 2 H pluses plus SO4, 2 minus. SO4, 2 minus. I kind of butched this just a little bit, not too bad. So, let me see if I have a different color other than blue. So do you see now when I break that apart, where if you look on both sides of the arrow, what does it look like I might be able to delete? K plus, spectator. Yep, very good. There's one more. Yep, SO4 2 minus. Very good. It seems like a lot of to do, I don't say for nothing, but we're kind of looking at the concept of removing spectator ions to now give us a net ionic equation. So I'm going to go ahead and show you now what this looks like without those. So without those, my net ionic equation would look like this. I'm still going to have my H2C2O4 dissolved in water, AQ. And now for this right here, this KMNO4, I'm only going to have the MNO4 minus. And now for my H2SO4, I better leave room for the stoichiometric coefficients. For my, I'll go ahead and put an AQ there. For my H2SO4, no SO4, so you're just looking at H plus. I'll go ahead and put AQ. And then on the product side, we still have our CO2. We still have our MN2 plus. And we still have our H2O. And if you were to balance this, you end up with, and it's on the slide coming up, 5 moles of your oxalic acid, 2 moles of your permanganate, 6 moles of your H plus, 10 moles of CO2 formed, 2 moles of manganese formed, and 8 moles of H2O formed. So these next slides, and I'm not sure what you guys want to fill out, but this slide, I don't know, I never know exactly what you guys have. This slide actually is what I put on the board there with regard to balancing it. When I taught, this is the first time I've actually tried to teach it this way, because sometimes I get to this slide and they're like, well, what's the difference? What? I don't see the difference, but this is your net ionic equation. What is it missing? It's actually on the next slide. What it's missing is the potassium and the sulfate. Why? Because they're the same, they're unchanged, they're just spectators. Okay. The one thing that's different is, and my bad, it's Gen Chem 2 thing, but actually H2SO4, sulfuric acid, you're like, dang, that's bad stuff, and it kind of is. But the way it ionizes or breaks apart, it doesn't give you 2 H pluses. Instead, it gives you 1 H plus, and then instead of the SO4 2 minus, it gives you the bisulfate ion, HSO4 minus. So anyway, we'll talk more about that in Chem 2. Sounds like you guys got it. So with all of that in mind, let's revisit the problem. So this is the chemistry we have going on in this situation. And what we've been doing before is to take the information from the problem and put it under the balanced equation. So that's what I would do again. So for right here, I would take that 0.2585 grams and I would put it right here. And then, let's see, the other piece of information I have is about the KMNO4. Well, in my net ionic equation, I don't have KMNO4, but I have MNO4 negative 1. So actually, under here, I'm going to write KMNO4 because that's what gives us our MNO4. And I'm going to say the volume is 22.35 milliliters. I'm going to put question mark molarity. So that's from the original problem. So, I don't know if you can see it yet, but once you do these a few times, you're like, oh, okay. Well, in this sort of problem, if you're given the mass of a reactant or a product, we know we can go from mass, 0.2585 grams, to moles, how can we do that? Molar mass. I'll put MM here. Yep, the molar mass. Well, we can go from moles of H2C2O4 to moles of MnO4 negative. How can we do that? Right. I heard stoichiometric ratio. Exactly. The 5 and the 2. Yep. Stoich ratio. Cool. Well, then this, it'll be easier to show you than to describe it. But once we have the moles of the MnO4, wait, that'll give, sorry, that will give us the, yeah, that's right. Once we have the moles of the MnO4, do you see where we can get to moles of KMnO4? Moles of MnO4, -1, the anion, to moles of KMnO4. And I'll go ahead and write down the ratio. It will look like this. For every 1 mole of the ion MnO4 -1, how many moles of KMnO4 do we have? What do you think? For every 1 mole of MnO4, how many moles of MnO4 would there be in one? Well, I can't answer my question. My own. Just 1. Yeah. And then once we have moles of KMnO4, do you remember how we divided it by volume to get molarity? Moles. Molarity is moles divided by volume. Granted, we have milliliters, we have to fix it in liters, but we can do that. So broadly speaking, that's how we're gonna knock this out. So again, if you're given the mass of something like this, don't freak out. You know you can go from mass to moles using the molar mass. All right. The one thing that's wrong with my with this is here you guys told me I need the molar mass of H2C2O4, and I don't have it in my builds. So you guys told me I'm going to use the molar mass is going to be my next term to get from grams of H2C2O4. And you guys would have to show this in your homework, but I'm telling you right now, it's 90.04. So here's the molar mass of H2C2O4. 1 mole of H2C2O4 over 90.04 grams of H2C2O4. Then you guys told me I could go ahead and do a stoichiometric ratio. So what does that look like to get the moles of MnO4 negative? Yep, 5 over 2. Wait, 2 over 5. 2 over 5, yep. 2 moles of NO4 minus over 5 moles of H2C2O4. Cool. Very good. So now we're at moles of MnO4 negative. So how did I say we're going to get to moles of KMnO4? 1 over 1, yep. 1 mole of KMnO4 over 1 mole of MnO4 negative. Well, this is exciting. How many siblings? Seeing 4 figures. That is correct. So 0.001148 moles of KMnO4. I just feel like I'm doing like the alphabet, LMNOP, KMnO4. Okay, so to get to molarity now, all we got to do is revisit what we knew about the KMnO4, and we knew it was 25.35 milliliters. So we're going to take those moles and divide it by our 22.35 milliliters. And that'll give us moles per milliliter. How do we get it moles per liter?
How many milliliters of oil?
Yep, 1,000 milliliters over 1 liter. Big deal. 4 sig figs again? I think so. So with 4 sig figs, you're looking at 0.05138. 0.05138. And the units would be molarity, KMnO4, or 0.05138 moles of KMnO4 per 1 liter of solution. Is that it? Okay, I can't. Like I said, it's been a year plus since I've done these, so I can't remember how many there are, but that's enough for today. And then we'll do combustion analysis on Wednesday. Should work great. Great. If I do say so myself.